All right, we're going to be going over some homework examples of how to combine functions in different ways. So the first couple here are combining functions with addition, subtraction, multiplication, and division. You can notice the notation here and the way that these are written, right? So for example, for our first one, where it's just f plus g of x, right? If we write that out, f plus g of x, that's the same thing as just taking two functions and adding them together, f of x plus g of x. It's really all we're doing here. Same thing if this was subtraction, we would subtract the function, multiplication, we'd multiply, so on. All right. So let's go ahead and go through these examples, kind of combine these functions in some different ways. So first one, we have two functions here. I'll keep this one pretty simple. So the first one that I'm going to do will be f plus g of x. So we're going to take f of x and add it to g of x. So that's 2x minus 5 plus 1 minus x. And this really just becomes a matter of combining like terms. So f plus g of x is equal to x minus 4, right? 2x minus x is going to be that, negative 4 and 5. All right, second one, we're going to go ahead and do subtraction. So we're going to do f minus g of x. You want to take note, I guess, that in addition, it doesn't really matter the order that we add them. We'll end up with the same answer here, but for subtraction, it matters slightly. It's going to make a difference which one we subtract. All right, so we're subtracting 1 minus x. We want to make sure we distribute the subtraction to the whole thing. So we end up with 2x minus 5 minus 1 plus x. And then kind of combining our like terms, our subtraction function will be 2x plus x minus 5 minus 1. Okay. All right, two more here. We're going to go ahead and do the product of these two functions now. So f times g of x. So that really just becomes these two things multiplying together. I want to make sure that we are distributing properly. So we're multiplying the 2x times both of these, and then the minus 5 times both of these. So 2x times 1 is 2x. 2x times minus x is minus 2x squared. Negative 5 times 1 is negative 5, and negative 5 times negative x is positive 5x. And then it's just a matter of making sure these are in proper order. So we'll do negative 2x squared plus 7x minus 5. So that would be our product of these two functions. Negative 2x squared plus 7x minus 5. I'm going to go ahead and erase this so that there's enough space to do the next one. Okay, next one is going to be the quotient of these two functions. So we're going to do f over g. Again, the order there matters, right? Which one goes on top, which one goes on the bottom. So we have 2x minus 5 over 1 minus x. Now in this case, if there were any common factors that we could cancel out, we might have to factor one of these and do that, but there's nothing here to do. So this would just simply be our answer. And then part E asks us about the domain of the quotient function. So in this case, for the domain, what we really care about is the numerator cannot be equal to 0. So the value that would make this equal to 0 would be 1. So x cannot be equal to 1. All other values are fine, but x cannot be equal to 1. That is the domain of f over g of x. All right, so we're going to go ahead and do this same process with just a slightly more complicated function down below. I'll go ahead and clear this right now. All right, so we're going to go ahead and do all 4 of those functions. So we have f plus g of x first. So f of x is this, x over x plus 1 plus g of x, which is just x cubed. Now, we could go ahead and add these together. We'd have to get a common denominator, because right now this is over 1. Doesn't really do much here. It can certainly be done. It's really up to you whether we would want to do it. I'm going to do it on this one, but maybe not on the subtraction one, just for that sake. So to get a common denominator, I need to multiply by x plus 1 on the top and the bottom here, so that I get x over x plus 1 plus x to the 4th plus x cubed over x plus 1. Now I can put these together into a single fraction so that we end up with x to the 4th plus x cubed plus x over x plus 1. And that would be our sum of the functions f and g. Not a lot nicer or simpler than just what we had up here in the blue, so do you really need to do it? Maybe, maybe not. It just depends on what we want to do with this after the fact. All right, the next one, subtracting these 2 functions, f minus g of x. So that's going to be x over x plus 1 plus, oh, not plus this time, we're subtracting minus x cubed. Now, same idea. I could subtract these. I'd have to do the same process here where I make these a common denominator. I guess I'll do it on this video, but not strictly necessary. Multiply by x plus 1 on the top and the bottom. So I end up with x over x plus 1 minus x to the 4th plus x to the 3rd over x plus 1. And then going ahead and putting these together, I end up with x minus x to the 4th minus x to the 3rd over x plus 1. And I suppose I could have rewritten this in order. Generally, we'd like this to be in descending order. So this one would just be onto the end over here. And so that's what we would end up with for our subtraction of the functions f and g. Not too bad, but is it really that much simpler than this? I don't really know. All right, next we have the product of these 2 functions. So f times g of x. And that's going to be x over x plus 1 times x cubed. Multiplying that, right? Remember, this is really over 1. So we're going to end up with x to the 4th over x plus 1. That'll be our product. And then the last combination was the quotient f over g. So we have x over x plus 1, that's f of x on top, over x cubed. Now, when you're dividing, you could think about it as multiplication by the reciprocal. So that's what I'll do here. So instead of dividing by x to the 3rd, I can multiply by the reciprocal of that, which would be 1 over x to the 3rd. I'm going to go ahead and leave it factored out. So that's going to be x over x to the 3rd times x plus 1. The reason I'm leaving it factored out is because I do want to keep in mind what values would be issues, what values would cause errors in our domain, because we would be dividing by 0 or something. Like not simplifying things out, I'm not simplifying out any excluded values out of our domain. But in this case, it wouldn't matter because 0 is a triple root for the denominator, but x equals 0 would not be allowed, and x equals -1 would not be allowed. Now, those were the only two numbers that are not allowed in the domain of this quotient function. Okay, go ahead and clear that off, and then we're going to move on to kind of the most important part of this lesson, where we're talking about the compositions of functions, where we put one function inside of another. So this is one notation for it. Another way to write f of g of x like this is to write it as f of g of x. So this is the same thing as this notation right there. I'm composing the function g inside of the function f. And then for this other one, g of f of x, that is where I'm putting f of x inside of the function g. So I'm going to go ahead and do this one first. So I'm putting g of x on the inside. So I'm actually going to be thinking about it this way. Instead of g of x, I'll just go ahead and put the function rule, x minus 1, in place of that. So I'm putting x minus 1 into the function f of x anywhere there's an x squared. So that anywhere there's an x, so it becomes, instead of x squared, it's going to become x minus 1 squared, right? Where the input goes, I'm putting in the function g of x. Then it's a matter of going ahead and multiplying that out. X squared minus 2x plus 1. That is our function f of g of x. So that's our composition function in kind of that order. Now, alternatively, we can go the other way. We can put f on the inside instead, and so that's going to look like this. F of x is simply x squared. So I'm going to take the function g and input x squared. So anywhere there was an x, I'm going to be putting x squared. I'm going to be putting the function f of x. So there we go. I've input that in there, and now I'm simplifying this. There's not really a lot of simplifying to do. This is our composition g of f of x. Similar, sort of. I mean, they're both quadratic equations, but fairly different. And most of the time when we do compositions, unless they happen to be inverse functions or something else is going on, we're going to get different equations depending on if we put f inside of g or g inside of f. All right, and let's do one more example here along sort of the realms of this difficulty. So we're going to be doing, first we'll be doing f of g of x. So g of x being this, so we're doing f of x cubed plus 1. So I'm going to be writing the function f, but instead of the x variable, I'm going to be putting the function rule for g of x in there. So that was going to be x cubed plus 1. All right? Same as the function f of x, but instead of x, we're replacing it with this more complicated input, the function g of x. All right, so now there's nothing really to do with these parentheses, so they more or less might not be there, don't need to be there really. So we have a plus 1 and a minus 1 that can just cancel out, become 0. I end up with the cube root of x cubed. Cube rooting, cubing are opposites, so overall our function f of g of x simplifies to just x. And in next section, we're going to learn that that's actually a special result. That means that we're likely to have what are called inverse functions here. All right, let's go ahead and do the other one, the composition in the other order. Now, if we're really wanting to know if these truly are inverse functions, we need to show both ways that we get x. So we'll be doing this a little bit more. So I'm doing g of the cube root of x minus 1 So I'm taking my function g, x cubed plus 1, and I'm putting in the cube root of x minus 1. So obviously cubing and cube rooting cancel each other out nicely. You end up with just x minus 1 plus 1. Minus 1 plus 1 becomes 0. So we end up with x again. So for both directions, when we compose these functions, we ended up with the same thing. So this, as I was alluding to earlier, this would be confirmation that these are inverse functions. Okay. Let's go ahead and clear this. And move on to just a couple more tougher examples of composition functions. I'm actually going to space this out a little more. Okay, so for the first one, we are going to find f of g of x and g of f of x with these two functions and just kind of see whether they are the same or not. Like last time they were the same, you know, the first time they weren't. We're going to see what happens here. So f of g of x. So in this case, we're putting g inside of f. So where the x is, I'm going to be putting x squared. So this ends up being x squared plus 4. Kind of shortcutted that a little bit right here. Was where the x was, and instead I put in the function rule for g of x. You don't have to do all the steps I did before if you can kind of see it going a little bit better, and kind of do this a little bit in shorter ways. Right? I skipped a few steps here. Looking at this, there's not really anything I can do with that. I mean, I can get rid of the parentheses. The parentheses don't really do anything here, but this would just be my composition. There's really no further simplification I can do to that composition. And then let's go ahead and try it the other way. So for this one, I'm going to be going the other direction. I'm going to be putting f inside of g. So instead of having x squared, I'm going to be having this for the input. All right, so we're putting in the function f of x where the x variable was in our function g of x. So here we can see that the square root and the squaring are going to cancel out. So we just end up with x plus 4 is our g of f of x. Now, they look like they're fairly different, but they're not all that different, right? I mean, because we were able to take the square root this time and get that squared gone and everything. Or the squaring, got rid of the square root, whereas this one, they're kind of both taking place. We know they're kind of counteracting each other, but because of the way we would simplify this, we can't actually simplify this, but very similar functions, just, you know, not the same. In this case, they are not the same. They're not equal to each other. So later on, we would know these are not inverse functions. They didn't both simplify to x. It does ask us to use a graphing utility, and I'll come back to that at the end. So I'm going to go ahead and move on to the very last one here. Scroll down. Okay, so we have these two functions. F of x is x to the 2/3 power, and g of x is x to the 6th. Yeah, x to the 6th. I wasn't sure if that was a negative or not. So let's do f of g of x. So that means we're putting g inside of f. So where I have this function here, x to the 2/3 power, I'm going to be putting in g, x to the 6th. Okay, using my exponent rules, I know that I'm supposed to multiply my exponents. So 6 times 2/3 is 12/3, and 12 over 3 actually just simplifies to be 4. So this is x to the 4th. And that's as far as I can go with that one. That is my composition function for f of g of x. And then last one here, I'll do this composition the other way, g of f of x. This one, remember, we're putting f inside of g. So g is x to the 6th, and then inside of it, I'm putting the other one, f, x to the 2/3. Same idea is happening here. I'm multiplying my exponents. That's kind of what we're supposed to do here. So we know this one is also going to be x to the 4th. So in these cases, the composition is the same. Again, in the future, when we're doing inverse functions, that doesn't mean these are inverses, because if they were inverses, they would both just be x, not x to the 4th. But they are the same, which is something that doesn't always happen. All right. Yeah, I'm going to go ahead and stop there. And hopefully this was helpful. Please email me if you have any further questions. Bye.